Some of you proposed solution. That's nice. So we can start having a look to them. Just for the sake of everyone, let's just remind everyone what we are going to do now is to practice on the exercises of the two lectures we had this week, so 13 and 14. So basically they are about basis, dimension, subspaces, and vector spaces. So this is quite a lot of material to do. And, just to be sure, what is a basis for a subspace of Rn? So the idea is that I take inside some Rn, a subspace. Then I take a set of elements inside V and is called a basis of V if two property holds, B1 and B2 hold. And just for our reminder for us, what does it mean, property B1 and property B2? Well, it is our convention to say that B1 says that the vector generate V, the subspace V, so the linear span of V1 VR is actually V, and that these vectors form a linearly independent set. And we also know that when you have a basis, they all have the same number of elements. And the number of elements in a basis is called dimension. So the dimension of V comes from the number of elements of any basis. Okay, so let's see now about our exercises. So what we want to do. So the first one is this one. We have a subset X, Y, Z, and T. So this is the number 2 of the first one, 7.1. These are 4 tuple of real numbers, so we are in R4. And we want that this equation is satisfied. So, and then we are asked to compute a basis and the dimension of V. Before doing that, just a pre-question. We should ask ourselves, is V a subspace? Of R4. So this is the pre-question we have to ask ourselves before computing, okay? So if you're asked to find the basis and the dimension, well, the object is going to be a subspace. In the exercise is said it is, but we want to practice also this definition. So is it a subspace or not? Well, the answer is going to be yes, but how do you prove it? Why is it a subspace? Do you have a quick way to convince me that it is a subspace? Okay, Jean Herrera has a nice answer. It says, well, it is a solution space. So yes, because V is the solution space of the linear system of equation having just one equation, which is this one here, right? Okay, so We can also write it, I hope you agree, as a kernel. So hence, V is a kernel. And can you tell me the kernel of what matrix? So what size this matrix should have, first of all? How big is the matrix giving V as a kernel? So let's see if you can tell me this. Yes, 1 times 4 is a good option because it is a linear system, the one we want to solve. This one, it is a linear system. Here you see, oops. Oh no, it's too, well, I don't know. I was playing with the setting, it's probably nice, who knows. So this equation gives a linear system, one equation of 4 unknowns, so it is actually 1 times 4, so that's nice. And the matrix is just 1, minus 1, 1, minus 1. Okay? Okay, so this is the matrix, if you want to give it a name, A 1 times 4, whose kernel is V. Okay, and then let's see what we remember about computing a basis and computing the dimension. Sometimes it's possible to compute the dimension without computing a basis, because you can use other results. For example, the Rusche-Capelli propositions theorem gives the dimension, well, it gives dimension of V without computing a basis. Computing a basis. And how does it work? Well, the exercise, the question I have here is with the minus. So, and this should be the latest one you have. So 7.1 second part. So let's say we do this one. You see this one here. And so it is with the minuses. Yeah, like the one we have here. So I don't know exactly, yeah, what you're looking at. Maybe it's an old version. Okay, so how do we compute the dimension of V without finding explicitly a basis using Rusche-Capelli theorem? Do you remember how to do this? So how is this done? Of course, this is something you have to know because it's now something we assume to be part of our knowledge. So how do we count the solution of a linear system of equation, homogeneous or not? Let's see. Exactly, Rusche-Capelli theorem tells you that you have to evaluate the number of free parameters. So the dimension of V, is just the number of unknowns minus the rank of the matrix of coefficient, which in our case is 4. And what is the rank of A? I think you agree with me that the rank of A is 1. And so we see that the dimension of V, by using Rusche-Capelli theorem, is 3. Okay, let's have a look in the chat. Well, yes, Giancarlo Herreras, you got it reversed, right? Because the rank is always less than the number of variables, so that the number you wrote is negative, so it's the other way around. Parnian Borugen is just, well, yes, you use the rank. Then Giuseppe Cerami has a question. He says, kernel, well, let me read. Probably I'm missing something, but isn't that ker A, excluding some possible values that could be in a subspace. For instance, 5, 4, 6, 7 is a vector that lies in the subspace, but it's generated by a combination of the kernel. I actually have no idea of how to answer this, Giuseppe Cerami, because I'm a little bit confused. So you say that the kernel is missing something. Well, the kernel is defined as the solution space. So the kernel, let's see if you're on the same space here, the kernel is the set of vectors such that AX equals 0. So I get all those vectors. So when you say some vectors are missing, what do you mean by that? So I'm curious to see what you mean by something is missing. Anyway, we got, so Giuseppe Cerami just tried to explain a little bit better what you mean. I don't know if rewriting what the kernel is help you here. But actually, yes, I don't see what you mean. 5, 4, 6, 7, yes, it is a vector in the kernel, but I don't see why you say it's a vector of the subspace. I don't see why you say it's not in the kernel. I hope you don't mean that the kernel is generated by this vector. It's not. That's the row space, right? Okay, maybe I see what you are doing. Are you, by any chance, exchanging row space and kernel? Because that's a typical mistake I see people do in this content. So just think about it and let me know if you're using the row space of these instead of the kernel. Because now we go and write down the kernel and you see that the vector you are saying is in the kernel as it is in V, and actually they are equal. Okay, so now how do we find the basis of V? Well, a basis of V you get by solving the system AX equals 0. So if you want to use our, fancy matrix notation, I want to step reduce this matrix, which is already step reduced, right? And there is exactly one marker. So it means that, for example, variable X, I will compute using all the other variables, Y, Z, and T, which are the three free parameters of Rusche-Capelli theorem, right? I'm reading in the chat again, but Giuseppe Cerami, I repeat this. Think of this. Are you speaking of the row space of this matrix? Because the kernel is not the row space. They are two different objects. So ask yourself, what is the row space and what is the kernel? From what you're saying, it looks like you are mixing the row space and the kernel, because the kernel is what we are computing now. And you will see, to compute the kernel, you need to solve the equations. So you will compute X using the rest. So you get it is Y minus Z plus T. And so when you write down the kernel as a set, to make it easy, it is the set of Y minus Z plus T, Y, Z, T, such that Y, Z, T are real numbers. Okay? And if you write it in this way, you can now do two things. So there is the old remark we made many, many times, that this vector is Y times 1, 1, 0, 0, plus minus 1, 0, 1, 0 times Z, plus T, 1, 0, 0, 1. Okay, so let's see if this is correct. Y, Z, T, yes. Okay. And in doing this, you get that the generators you want are these three vectors here. How do you produce them? Well, you just look at the three free parameters. You set 1 = 1, all the rest equals 0. You get the first one. Then you set z = 1, and you get the second one. And then you get the third one by setting t = 1. So let me just finish this. So the kernel of A is the linear span of these three vectors, 1, 1, 0. Then there will be -1, 0, 1, 0. And then there will be 1, 0, 0, 1. Okay, here are the three vectors, v1, v2, and v3, that generate the kernel. Then how do you go and produce a basis? Well, you should go and reduce the matrix having these three as rows. Okay, you should go and reduce the matrix having these three as rows or columns, depending on what you prefer to do. Okay, but if you do that, just let's consider the matrix having these as columns. Just a second, and you will see why we do that. So it's 1, 1, 0, 0, -1, 0, 1, 0, 1, 0, 0, 1. And you see this matrix is step reduced. And these three are markers. So this matrix here, call it matrix B, has rank 3. Okay, and the matrix you should step reduce to see if it is a basis is the transpose. So you see V1, V2, V3 are linearly independent because this matrix here has rank 3, because when you take the transpose, the rank is not changing, as we already saw. And this means that the set V1, V2, and V3 is a basis of the kernel. So is a basis of the kernel of A. And this is probably very close to the answer, exactly the same answer that Jean Herrera produced. Okay, let's have a look in the chat. So Giuseppe Cerami looks like he understood what the problem was. Samuele Cravero says, so the two kernels are equivalent. So Samuele Cravero, what kernels are you speaking about? Because I only see one. I only see the kernel of A. What is the other kernel you are referring to? Can you tell me so I can understand your question? In the meanwhile, of course, any other question about what I did is welcome. But what kernels? Why two? Why two kernels? Okay, so it was an ongoing temporary confusion. Okay, good. So we found a basis. No, there's no need to be sorry. It's, you know, in a room, you can raise your hand and, you know, that's the same thing. No harm in asking. And very often I tell this to everyone, sorry. If you have a doubt, many other people have the same doubt usually. So asking is always a good process. Okay, now let's go a little bit farther. So, you know, just to answer Giuseppe Cerami question. So Giuseppe Cerami was saying, well, I take the vector u, something like 5, 6, no, 5, 4, 6, and 7. And this is inside V. Well, let's check. I don't trust Giuseppe Cerami, so I want to go and see. So I go and see, why is it inside? How do we answer? Well, you have to go and look at the equation and see if it is 0 when you substitute, right? So I just write 5, 4, 6, and 7. Then I sum these two, I get 11. I sum these two, I get 11. So the answer is yes, Giuseppe Cerami is right. It is true that this vector is inside V. But if it is inside V, then it must be a linear combination of V1, V2, and V3. So hence, U is a linear combination of V1, V2, and V3. Okay. Now, in this situation, is not difficult to see what you have to do, because you see, the last component of any linear combination of these three only depends on V3, right? And the second component only depends on, and the third component only depends on V2, because I have a 0 here, a 1 here, a 0 there. So this number only depends on V2. And the second component only depends on V1. So this number only depends on V1. So how can I get U as a linear combination of V1, V2, and V3? Can you tell me what numbers should I use? U is some number V1 plus some number V2 plus some number V3. Can you tell me what are these three numbers? 4, 6, and 7. Exactly, because the number I have to put here is 7. And the number I have to put here, it is 6. And the number I have to put here is 4, for the argument we made before, that they are only changing one component at a time. And well, but then if you do this, then the first component of this vector is going to be 4 minus 6 plus 7, which, if you go and check, is actually 5. The second component is 4, the third component is 6, and the fourth component is 7, exactly as we needed. But that's only true because the equation is satisfied. So it's always useful, at least at the beginning, to check that what you obtain as a logical consequence of theorem, axioms, proposition, and so on is actually true. So it's a very good idea to go and compute, to go and check that the result you obtain is actually correct. What should be, it is. Okay. Any further question about this exercise before we move to the last of 7.1? So there is a question of Ishanpon Manikandan, and he asked about the kernel of a subspace and the kernel of A. The fact is that there is no kernel of a subspace. You know, the kernel is, for the moment, only of a matrix. So I can say that there is no way of answering your question because there is no kernel of a subspace. When you speak of a kernel, it must be of a matrix. This is a matrix, and the kernel is equal V. So maybe you want to say, what is the difference between V and the kernel of A? No difference, because V is the kernel of A, because we constructed A in such a way that this is true. Okay, so now let's move to the last of 7.1. So same question for B, given by the vectors in R3, such that V cross 1, 1, 1 is the 0 vector. And again, we want to compute a basis and the dimension. Okay, just let's play a little bit with the geometry of the situation. So I have this nice vector here, call it U, in 3 space. So here is vector U. And I'm looking for all vectors which give cross product 0 with respect to U. What kind of geometrical object is that? Can you draw V in R3? What would you expect to see? So while you think about how to draw V, I go on and see in the chat. So Salvatore Lagrasta says, why do we need to see if the rank of B transpose was equal to the rank of B to state that the columns of B were a basis of B? There's no need to do that, Salvatore Lagrasta. The fact is that if you remember, I told you, if you have V as the linear span of some vectors, you put them as rows, you row reduce. Because we always row reduce, we don't column reduce. It's just a convention. So this was just to see you, to show to you why the rows are independent. Because they are independent if you write them down as columns, because the rank can be computed by columns and rows, and a matrix and its transpose have the same rank. So it was just a way to convince you that the rank of the matrix having the vectors as rows is 3 without computing it and using the fact that the rank of the transpose is immediately seen. So this is the transpose and the rank you see immediately is 3. If you write these as rows, it is not row reduce and you have to compute. Okay? Okay, in the meanwhile, many people answer the question, what is the space V? Well, it is the line going through the origin and parallel to V. Okay, so this is how I summarize your remarks. Okay, so the idea is that V is a line through the origin. So it is a subspace. And you can tell me the dimension and the basis, right? So thus it is a subspace. Of dimension something. And now you tell me having basis. And now you tell me a basis. So what is the dimension of V as a subspace of R3? So it's a subspace of R3. What is its dimension? Yes, it is 1. It's very natural that a line is an object of dimension 1, right? And what is a basis? Maybe Sofia Karnauk knows. What is a basis of this one? Yes, 1, 1, 1. But why the question mark? Why the doubt? So what is confusing us? Well, this was a quick way of seeing what the answer is by some geometry, and that's perfectly fine, but then there must be no question marks. Arsh Baraji suggests something different, and it says, well, let's look at V. So, and I look at a vector here with components x, y, z. Then I compute V cross U. And what vector is V cross U? Well, you can do this in many different ways. For example, we can use the usual matrix to compute a cross product. And in this case, you will get what the cross product is. So it's going to be Y minus Z. Then it's going to be Z minus X and X minus Y. And we want these three to be equal 0. So you see V is the set of vectors X, Y, Z in R3 such that Y minus Z is equal Z minus X equal X minus Y equals 0. So basically, to find V, I have to solve the linear system of equations, which is Y minus Z equals 0, X minus Z equals 0, X minus Y equals 0, or if you want, Y equals Z, X equals Z, which you can also write as Ash Bairaji did, as X equal Y equals Z. Only one line, but it is two equations. So you see that V, if you don't realize it is a line, and that's a pity if you don't, because you should develop some geometric intuition from this class, but suppose you don't, then you can, however, see it is a solution space of a linear system of equations. So it is a subspace, and it is also a kernel. So doing all this interpretation is not to confuse you, right? It's to make life easier, because using different interpretation, you have more tools to answer to our questions. And here is the matrix presentation, if we want, right? Is the kernel of this matrix here, or of other matrices you can take as linear combinations of these two. Okay, so by writing it in this way, say as a solution space of a linear system of equations, or as a kernel, we can now use the tools we have learned now. So by Rushet-Capelli theorem, I can say what is the dimension. So dimension of V is number of unknowns minus the rank of A. And I hope you agree this is number 1, as we computed before, right? And also, I can find a basis by looking at the kernel as a solution space. So I have to find the values of X, Y, Z satisfying this equation. But you see, they are of the shape Z, 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 such that Z is a real number. And now this is the linear span of 1, 1, 1. Not a surprise, right? You just factor Z out. And since you have only one vector, which is not 0, the set formed by that vector is a basis. So hence, here is a basis of V. Okay, and this is probably, let's see, at the beginning, Jean Herrera produced, yes, he got it correct. He said B basis is here, and the dimension is 1. Okay. Okay, good, good. Okay, any question about what we did? And you should note that now everything is coming together. Matrices, linear system, ranks, geometry, and they are all tools that if you have, you will have a much, much easier life than if you don't. Okay, so probably this is a good time to be scared and say, well, I'm not following, I'm missing something. And that's true. And if you want not to be completely lost, you need to fill all those gaps as soon as possible. Okay, any question about how we solve this one? Okay, give you a few minutes to think about questions. Okay, we have a question by Daniel Caldiero, who says, how did we find matrix A? Well, matrix A is the matrix of coefficients of this system of equations, or if you prefer, of this system. The one we found is of this system here. So it's just writing down the matrix of coefficient of a linear system of equations. Not a big problem, right? This is something we know how to do. How do you find the system? Well, by computing the cross product, is using the definition of the set V. Okay, good. So let's see the next one. The next one was about finding basis and dimension of row space, column space, kernel of a bunch of matrices. Okay, so let's just write down one in particular. So matrix A, this one here. Okay, so let's see how you do this. I'd like you to try. So I give you, say, 2 minutes so that you can try this by yourself and come up with, a possible answer, and then we can compare. So the row space, the column space, the kernel, basis, dimension, and as we said before, sometimes you can compute the dimension without computing the basis. There are shortcuts sometimes that you can use. Okay, so Air Fanfare has some suggestions. Okay, so let's go with the first suggestion. So what is the rank of matrix A? The rank of matrix A is 2, right? This means that, for example, the kernel, which comes from Roche-Capelli theorem, is going to be 2 minus 2, which is 0. And there is only a subspace. Yeah, exactly. There is only a subspace having dimension 0. So this means that the kernel is the 0 subspace of columns vector. Okay, then if you remember, the rank is also telling me the dimension of the row span and the column span, because the dimension of the row span, which is always equal to the dimension of the column span, is equal to the rank. So it is equal to. Now, okay, sorry, something is a little bit lagging here. Okay, now it's going. So they have dimension 2. Now let's play a game for a second. Row space is inside R1, 2. Okay, now let me ask you, what is the dimension of R1, 2? So the dimension of row matrices, 1 row and 2 columns. So let's see, what is the dimension of row, of R1, 2? Well, Samuele Cravero says 1, but that's not probably correct, right? Because how do you find a basis for this? It is just like this, right? These two row space, row vector, produce all row vectors, right? Exactly, so the dimension is 2. No question about this, right? So this equality gives that dimension is 2. Exactly. Now, this is the same dimension of row space. So you see, row space of A is inside R1, 2, and they have the same dimension. So what do you think is going to be the row space? So what do you think is going to be the row space of A? So you have two objects, one inside the other, having the same dimension. So what do you think is the row space? Can be anything smaller than R1, 2. The row space is the all or R1, 2. Yes, it's the same as R1, 2 because they have the same dimension and one is inside the other. Similarly, the column space of A is R21 because the dimension of the column space is 2 and R21 has dimension 2. So let's make a note and say that if you have V1 and V2 inside some Rn subspaces, well, no, I don't want to say this. I want to say that you have this, V1 inside V2, inside Rn, V1 and V2 are subspaces. If they have the same dimension, then they are equal. So you see, there is this kind of magic. By comparing these two numbers and getting that they are the same, you get that the two subspaces are the same. And this comes from the fact that if they have the same dimension, they must have a basis with the same number of elements. So a basis of V1 is going to be a basis of V2 also. Okay, so why is this the case? It's very simple. This is true because V1, VR, a basis of V1 is also a basis of V2 because they have the same dimension. So R is the dimension of V1, but also the dimension of V2. So these elements, which are linearly independent inside V2, are also a basis, and they generate all of V2, and so they are equal. Okay, now let's go back to our exercises about this prescription. If you don't have doubts, question, or remark about this part, we'll go and change a little bit the starting point in a way that probably you already did, because this is the one I asked you to do at the beginning. So I changed this matrix by putting a minus also here, okay? And now we consider the same questions. Basis, dimension for these subspaces, row space, column space, kernel. See what you can do. Okay, so let's see. Okay, perfect. So you probably learn now to do this now. So the rank of A is 1. So this means that the dimension of the kernel is 2 minus 1, which is 1. And the dimension of the row space, which is always equal to the dimension of the column space, which is always equal to the rank, is always equal to number 1. So all dimensions are equal 1. Yes, they are all equal 1, also for the kernel. So probably Sophia made, Karnaut made something wrong in computing the kernel. The matrix now is this one. So there are 2 minuses here, right? 2 minuses. Okay, so what is the kernel? Well, I need to solve the linear system of equation. And since the dimension is 1, I just need to find one solution, which is not the trivial solution, the 0,0 solution, and it will be a generator. So here is the kernel, and this is a basis. So this is a basis. What about the row space? Well, the row space, again, it has dimension 1, so just any non-zero row will do. And this will be a basis basis for the row space. And finally, the column space of A, again, it has dimension 1, so just any non-zero column will work, and this is a basis. So basically, having dimension 1, it means you just need to produce a non-zero element inside, and that will work as a basis. Okay, good. Okay, so looks like that we mainly agree on this. So we can move to something slightly different if you don't have questions or remark. So I write this. So now we have these subspace, so x, y, z, t in R4, such that the sum is 0. And then there is a question which says, if possible, find a basis of V containing the vectors 1, -1, 0, 0, and 1, -1, 1, -1. So now you see, you don't need only to find a basis, but you want to find a basis containing these two vectors. First, you have to check that these two actually belong to V, because if they don't belong to V, well, then the answer will be it is not possible. But in this case, you see, they do belong to V, and here there is an equal sign missing, sorry. So in principle, it is possible. It was not so easy to dismiss, saying, well, it is not possible. So what we should do is to see what is the dimension of V. And well, I know it is 4 minus 1 equal 3, because V is a solution space. So it's a kernel of a matrix with all ones coming from this linear system, right? Rank 1, 4 knowns, rank, the dimension is 3, yes. So let's see in the chat for a second. Can we also write 1, 0 for the basis of the column space? So there is a question about here. Well, of course not, Michele Porcu, because you see that 1, 0 does not belong here. So it's not that it is not a basis, it's not an element of the column space. So what is the problem? The problem is that you cannot row reduce and then look at the columns. So what you did probably is row reduce A, get the matrix 1, 1, 0, 0, second row 0, 0. But then this you can use to compute the row space. You can use to compute the kernel, but not the column space. That's not what you can do, okay? That's another typical mistake. But if you go and see, it's not true that the column space of row equivalent matrix is the same. The dimension is the same, but it is not the same space. Okay. Let's see now how to do this. So to find a basis, we need to produce 3 elements. And we already have 2. So we would like to write down a basis made by these 2 vectors, which are the one given to us, V1, V2, and I need to find U. So find U such that V1, V2, U is a basis of V. And what do I need to do? Well, what I need to do is to find U. So it is enough to find U not belonging to the linear span of V1 and V2, but belonging to V. So it is enough to find U not belonging to the linear span, because we want to have linear independence, but belonging to V. So I hope you agree that this is what you need to do, because this part will tell me that property B1 is okay, and this part will tell me that property B2 is okay, making this set into a basis. Okay? Yes, Generera, probably you answer some different question. Okay, so what do you need to do? Find U inside V, which is not a linear combination of these two. There are many ways of doing this. One way is to find all elements inside V and look for something which is not a linear combination of the first two, right? Or one can try to be smart and, for example, see that there are some special features of V1 and V2. But let's say I want to write down the all of V, and this is the solution space of the linear system of equations, x plus y plus z plus t equals 0. So this is minus y minus z minus t y z t, such that y z t are real numbers. So by following the procedure that now we know very well, I just set one free variable equal 1, all the rest equals 0. And in this way, I produce a basis. Okay, and here something is missing. Okay, and I produce a basis. Okay, so what you can see at this point, for example, you can see that this vector is actually V1, but V2 is not appearing in the list. But for sure, this vector here is not a linear combination of V1 and V2 because of having a 0 there and not a 0 down there. So this is a nice choice for vector U, which is not a linear combination of V1 and V2. So this is a way of doing this. So you write down V, and then by inspection, you look for elements of the basis which are not a linear combination of V1 and V2. So basically, this requirement here is that the matrix having as rows V1, V2, and U has rank 3. So you want U not to be a linear combination of V1, V2, and V3. And you can do this simply by inspection, trying this one, and you will see that if you put this element here, the rank is 2. You try this one, you compute the rank, you see the rank is 3, and you say, I can pick this one. But actually, you can also pick this one too, because if you put it here, you will see the rank is 3 again. Okay? Any question about this? So you find a basis, and then you just pick one element at a time and see which one you can select. That's a fail-proof way of finding an element that will give you a basis of V containing the two elements you started with. Okay. So if you don't have questions about this one, so a basis is given by this choice of U, V1, V2, and this U. If you don't have questions about how to do this and how this works, let's move to something else. And let's see some set V, say 2 by 2 matrices with real coefficients, such that the determinant of A is 0, and we ask, is V a R vector space? With the operations of R22. Okay, so basically the operations of R22 are the sum and multiplication by a scalar of matrices, right? So the usual operation. And we want to know if V is a vector space of R or not. So since we use these operations, all the properties of the operations are okay if V is closed with respect to the operation. So with respect to addition and multiplication by a scalar. Okay, so what do you think? Is V a subspace or not? Pascal Riaki says no, and also Gian Herrera. Can you tell me why no? So we have a, say, general agreement that it is not, but can you explain why it is not? Okay, so Pascal Riaki says, well, it is not because if you sum these two matrices, so this is a matrix of V, this is a matrix of V, and when you take the sum, this is not a matrix of V, because being in V means determinant 0. And the determinant of this matrix, which is the identity, it is 1. It is not 0. Okay, so what is the problem? It is not closed with respect to addition. Perfect, exactly. So you cannot take the sum of two elements of V and getting, again, an element of V. And so this is why the answer is no, because there exist A and B inside V, and A plus B is not inside V. So, for example, this is A and this is B. Okay, good. So let's try a slightly different one, in which now we look at polynomials of degree at most 3 in variable x, such that P of 0 is equal 1. And we ask the same question. Is this a subspace? Sorry, is this a vector space with the operations of polynomials? And again, you only need to check about what. Let's see if you know what you have to check and if you can decide whether it is or it is not a vector space. So Giuseppe Cerami says it is not. Why it is not? Jean Herrera says no, because the null polynomial is not there. And that's a good point. It is a good point, because if you use the same operation of R3x, this means that the 0 of R3x, which is the 0 polynomial, must be inside V. And here it is not true. So, but 0 is not inside V, since the 0 polynomial will never take value 1. Okay? Or Giuseppe Cerami says, this is the known term of the polynomial, and you can sum two polynomials having known term. So the part without x equal 1, but the sum is equal 2. So that's another good reason for saying that the answer here is no. And there are two different reasons for which the answer is actually no. Good. Okay, now let's see another one. So say, looking more or less like this. So let's put it here. Let's change what needs to be changed. And now we say that we want the, so we change the condition, and we want P prime of x to be equal x. So let's see if this is a vector space or not. So I think that Jean Herrera can say yes or no pretty quickly if you just look at the way you solved the previous one. Is this a vector space with the operations? Sofia can now say it is not, and she found two polynomials satisfying the property such that the sum is not there. That's perfectly fine. And again, 0 is not here. So you can say no. One reason is that 0 not in V. And another reason is that not closed with respect to the addition. Okay, good. Now you see, very often it is enough to look at some special elements to be able to answer these kind of questions. What happens if the answer is yes? So we can change this a little bit. Maybe I can put here 0. So we just change the condition. Now the first derivative must be the 0 polynomial. What do you think? Is this possible or not? Sorry, is this a vector space or not with the usual operations? Again, you only need to check closure. Looking for 0 is a shortcut for checking if it is a vector space or not. But what happens if 0 is there? So you see, when the answer is no, usually there are quite a lot of different ways to say is no. But what if the answer is yes? Like in this case, I think you start to suspect that the answer could be yes. But how do you check this? Well, since you're using operations inside R3, and R3 is a R3x, and it is a vector space, then it is enough to check for closure. And if closure is working, well, everything is going to be okay. So what you do, you take two elements inside V, and you ask yourself, is the sum inside B? And how do you answer this question? Well, you need to compute the first derivative of the sum. And what is the sum? Well, the sum is the sum of the two polynomials by definition, right? And what is the derivative of the sum? Is the sum of the derivatives. And if this is 0 and this is 0, then also the original one is 0. So yes, this implication is correct, because 0 plus 0 gives you 0. So it is closed with respect to addition. And then it is also closed with respect to multiplication by a scalar. And so all is going to be okay. Camilla Tetti, for example, checked the product. Okay, good. Yes, Giuseppe Cerami, there was the first derivative. Yeah, okay, so you can answer this question and say, yes, it is. And this is the reason why it is. Okay, any further question, doubt, or remark? Okay, good. So see you next week and have a nice day.